Let's look at horizontal stretching now. If we look again at our formula, general formula for our tan graph, we notice if we compare this to the tan theta over 2, we see that A is equal to 1, B is equal to a half, and H and K are both 0. So, suppose we take 90 degrees. So, at 90 degree will happen what happened divided by 2 at 45 before. So, at 90 degrees, we need to make a dot at 1. Because to get to 90, I must have 40 tan of 45, which is 1. And the same with, for instance, at minus 90 degrees, I will get minus 90 divided by 2 gives me 45, and I will read off that value. So, F goes to N and D goes to M. So, in this case, the graph becomes flatter. And if we look at what happens here, this value N is already on the vertical asymptote of the original graph, and so is the value at M here. So that means that in this case, the graph will stretch down here, go through the origin, go up there, and have a vertical asymptote. The red dotted lines will give me the vertical asymptote of that new graph. And so we can continue also for the next one and the next one, etc. So immediately you can see here, we will skip this part because we already used up all the horizontal values from minus 180 to plus 180. So the next 360 degrees, we will have our new graph, which will be here. Well, this one goes off there to its vertical asymptote. On this page, I've now joined the points, which I previously drawn in blue. It's now the red graph. And you can see it is also flatter vertically, but it's not because we squashed it vertically, it is because we stretched it horizontally. So if you look at the theta over 2 there, then our period will be 180 degrees times 2, which is equal to 360 degrees. And we can see here from minus 180 to plus 180, there we get a 360 degrees span. Again, we have no amplitude, and we have the roots. We have them at, we skip now some of the roots, so we skip B. We have definitely at E and at K and at something before B, which is not on the graph. So in general, or we can first write down the roots, they are at 0 and at 360 degrees, and we expect that the next one will be at 720 degrees because of the period. So if we now write down the general roots, we get theta equal to K times 180 degrees for the regular one, but now we multiply it by 2, where K is an element of Z. So that is our general roots. Again, we do not have any extremes, and the vertical asymptotes in this case will also be double what it was before. So in this case, if we first look at, for instance, at theta equal to minus 180 degrees, then we need to add K times 360 degrees. Where K is an element of Z. Again, we could just as well set plus 180 degrees if we look at H there. And to get to the new one, we can add 360K. So in this case, we can again write the formula plus 180, which gives us 2k plus 1 times 180 degrees, where k is an element of z. On this page, we again have a summary of what happened on the previous page, the period, and we see that the 2 here and that 2 there coincide, and that also coincides here. So we have the period now double, because it runs slower through this whole horizontal, the set of values here, or the degrees. It runs slower. We do not have any amplitude. We only see 2 roots here, but there are more. And what we saw here is 0 and 360 degrees, and we can assume minus 360 degrees part of that. And we can write down the general formula. We again say there's no extremes, because we don't have any minimum or maximum, because plus or minus infinity are not finite numbers. We can write down the vertical asymptotes first individually at minus 180, at plus 180, and at 540, and we can write down a formula for that. To finalize the vertical asymptotes, I see there's a typing error here, and we should have this 180 divided by 2, because we take out 90 degrees both times. And so the final answer will be then 2k plus 1 times 90 degrees. Finally, we can look at the concavity. We can clearly see here the graph is concave downwards, and on that side it's concave upwards. So the point E here is inflection point. The same with the point K, which is also inflection point, because it's concave up there and concave down there.